So, in this session we will be discussing about the details of these chemical catalysis or catalytic reactions. See, when we have discussed the introductory part of this catalysis, we have mostly focused on this competition between the pore diffusion and the surface reaction. However, we have not paid any attention to this adsorption, desorption in conjugations with the surface reactions. What are the different types of the surface reaction? And if you can again revisit what we have previously covered, there you can see that we have mostly replaced the rate equation in terms of the volume of the reactant, right. Initially what we have started with the per unit surface area basis specific rate equations, but using the equivalence that S into minus R A double prime is equal to this V into minus R A, we have replaced that, okay, in terms of minus R A, which is KCA. So, from there we have introduced this concept or idea of this Thiele modulus and derived the relation between the effectiveness ratio and Thiele modulus, where this effectiveness ratio is the rate of the reaction with pore diffusion divided by the rate of the reaction without pore diffusion. That is, if the reaction is being continued with the external concentration, external surface area concentration of this reactant, right. So, with that if you do that, so that is there is no effect of pore diffusion, and in the numerator the rate with pore diffusion. So, definitely if pore diffusion has got no effect or no role to play, then epsilon, that is the effectiveness factor, will be equal to 1, and where we have a strong pore diffusion regime, this epsilon nearly it's equal to 1 by MT. And the intermediate form, where neither it is the reaction controlled nor it is pore diffusion controlled, we have system specific functional relation between epsilon and MT. Just like for rectangular slab like catalyst pellet, we have the relation as epsilon is equal to this tan hyperbolic MT by MT, right. Whereas, in case of sphere it will change to 1 by MT into this tan hyperbolic 3 MT by MT, something like that, minus 1 by MT, right. So, we have discussed it, whereas in case of cylindrical catalyst pellet, it includes this or it involves this Bessel function of the second kind, right. So, here we will be mostly focusing on the competition between not the pore diffusion and reaction, but rather with pore diffusion, not pore diffusion, sorry, adsorption, surface reaction and desorption, right. So, again if you revisit the steps of the catalyst, so steps involved in catalysis. See, the first step is diffusion of the reactant through the external film. Right. Second, pore diffusion of the reactants. Third, adsorption of the reactant onto the active sites. Active sites of the catalyst. Four, it is the surface reaction. Five, it is desorption of the product. 6. Pore diffusion of the product to the external surface of the catalyst. Counter diffusion of products through the external film of the catalyst. So, you see that these are the 7 steps involved in a catalytic reaction. So, if we try to represent it pictorially using scale up version of this catalyst pellet, scale up drawing of this schematic of this catalyst pellet. So, this is the catalyst pellet, and here we have the streams of the reactant flowing, right. So, obviously, on the surface of this spherical pellet, we will have a formation of this film, right, through which the mechanism of mass transport is diffusion. See, at this surface, the bulk concentration of reactant is CAB. It diffuses to the surface. So, this is the external film, right. It diffuses to the surface. So, definitely a driving force is required and concentration will drop. So, this is CAS. Now, from here we will have a pore like this, though this is not the exact scale geometry, it is definitely it is scaled up. So, this is the catalyst pore. Now, let us say there is an active side here. So, this is step 1. Now, so it will reach the active side. So, this is step 2, right. Next, it will get adsorbed, step 3. Then a surface reaction will happen, step 4. Then desorption, step 5. Back diffusion through the pore, step 6. And finally, counter diffusion, step 7, right. So, these are the steps as we have discussed involved in the catalyst. So, definitely here the figure is bit jumbled up. So, if we redraw the schematic of steps involved in solid catalysis. See, this is the surface of the catalyst, not the external surface, this is the active surface, let us say hypothetical active surface. Active surface will not be like the continuous surface, there are active sites. So, anyway, let us call it the active surface of catalyst. Here this, or rather this solid one, this is the external surface of the catalyst. And here we have the film, external film. So, Here the concentration is CAB, it diffuses from, this is a step 1, CAS. Next, it is the pore diffusion, step 2. Next, it is adsorption, step 3, surface reaction, step 4, desorption, step 5, counter diffusion through the pore, step 6, and finally going out, that is step 7, through the diffusing through the external film. Right. So, here the surface reaction may be irreversible arrow product. Right. So, there are different types of surface reaction, we will discuss it later. So, these are the steps involved in the catalysis. Now, see, if we go for a general discussion, we can think of that okay, external pore diffusion may be the rate controlling. So, what will be the rate expression if the external pore diffusion or sorry external film diffusion is the rate controlling step. So, let us see. So, here external diffusion of reactant through the film is the rate controlling step. So, let us say the diameter of the pellet is dP and the velocity is u. Let the catalyst pellet diameter is dP and the velocity or the average velocity of the reactant is u. Right. So, if the diffusion through the external film is a rate controlling step, then the absorbed rate minus RA prime OBS, or minus RA prime, let us write minus RA prime because that is a rate controlling step, which means the slowest step. So, step or rate of this specific step may be confirmed as the rate of the overall process because the rate of all the other steps is insignificant compared to that specific rate. So, this is the sluggish most rate of this entire catalysis or entire in considering all the 7 steps. So, you see that here we will have minus RA, the notation, let me check the notation, Kc. So, Kc into CAB minus CAS, right, where Kc is the mass transfer coefficient. Now, Kc from film theory we can have this Kc as a function of dP, Kc we can write as dA diffusivity by delta. So, delta is this effective film thickness. thickness of the effective film. Right. So, now you see what is the influence of u and dp on delta. So, we know that whenever we are increasing u, delta must decrease, and whenever we are increasing dp, delta must increase. Right. So, if I think of parameter, let us group them into a single parameter u by dp. Right. So, how this observed reaction rate will change with the increase of u by dp? So, initially when the dp is pretty small, right, when dp is pretty small and u is high, so we have, or initially if it will be a high value of this u by dp term and delta will be abruptly low, and as a consequence there will be no resistance, right. So, this can no longer, this step can no longer be this rate controlling step. However, on the other hand, if u is small and dp is large, the external film diffusion through this external film may be the rate controlling. So, in that case we will have a sharp variation of this minus R A prime with this u by dp, right. Whereas, this variation, this observed rate will increase with the increasing value of this u by dp, finally leveling off to some threshold value. So, the trend of minus R A prime with respect to u by dp. So, this is, it is like this, u by dp and this minus R A prime, and it increases before leveling off to some constant value, right. So, in this, if we have the data or the point somewhere here, so obviously we can infer that external film diffusion has no role to play, and here it is external film diffusion controlled. So, if I have my data points for this system what we are dealing with somewhere here, we can say that external film diffusion is a rate controlling step. However, if we find it here, we can infer that external film diffusion has got no role to play. So, that is all about this external film diffusion. Next, it is the pore diffusion. We have already discussed it in terms of effectiveness and Thiele modulus. However, if I think in a consistent form as we have described it here, we can write the expression of rate in a somewhat different way. Okay. So, let us see. So, this is 1. Second is pore diffusion is the rate controlling step. Right. So, here the rate which is minus R A prime is equal to, let me check what notation I have used, Kr. So, Kr into Cas. Right. Now, how this Kr will vary, or observed rate, how it will vary? How it will vary with dp. So, variation will be like this. So, in this regime where there is a sharp fall of this observed rate, that means Kr actually is sharply decreasing with dP, right. So, in this region Kr is independent of dP. Right. So, it is pretty similar to this epsilon versus mt in log space. Anyway, so if the Kr has got a sharp fall with increasing dP, and why it will fall with dP? Because you see, this is the pore diffusion controlling regime. Right. So, here epsilon is 1 by mt as we have discussed, and mt is proportional to L, and L is in the order of dP. It will be dP by 2, dP by 3, or not dP, R by 2 or R by 3, and if it is a catalyst pellet of this rectangular shape, it will be this thickness by 2, right. So, you can see that with the increase of dP, this L increases, and as L increases, the telemodulus increases, and epsilon, which is the rate of the reaction with pore diffusion divided by the rate of the reaction without pore diffusion, that will go on decreasing sharply, right, with the increase of L. So, if my data point for the specific reaction what we are discussing falls here, we can say that it is independent of the pore diffusion, but if it is somewhere over here, we can say it is a pore diffusion controlling regime, right. So, with this two, let us now pass on first to quantify this process of adsorption, right. So, what are the different types of adsorption? What is the equilibrium relation, that is the adsorption isotherm in case of reaction? So, that we will initially discuss, and after that we will discuss these similar rate expressions for reactions, right, elementary rate expression, and finally for desorption. Now, we will combine, after we have introduced these rate expressions for adsorption, reaction and desorption. Next, we will see what will be the overall observed rate equation if the reaction is rate controlling, or adsorption is rate controlling, or desorption is rate controlling, right. So, next it is the adsorption of reactant onto the active site. Just right now we are not discussing about what will be the apparent or observed rate expression if this step of adsorption is rate controlling. Right. So, adsorption of reactant onto the active sites. Of the catalyst. Now, you see this A is the reactant, plus it will react with the active site S, leading to an adsorbed state. So, this is the active site, and this is the adsorbed state, right. Now, you see the total number of active sites, or we can say the concentration of the active site. First question arises, how to represent the concentration, because if I am writing this sort of stoichiometry, definitely we will express A in terms of either partial pressure or concentration, then S must be expressed in equivalent unit. So, S must be concentration. So, how to represent the concentration of an active site or of active sites. So, this is the concentration here is the number of active sites per unit mass of the catalyst divided by Na, and that is Avogadro number. Right. So, you see, whenever we are writing this, we are getting the concentration expressed moles of the active site per unit mass of the catalyst. Right. So, that is the way we represent the active site concentration. Next, the active site balance. Then initially we have a total number of active sites CT, some will be occupied and some will remain free or unoccupied. So, yeah, A dot S, C of A dot S. These are occupied if I have a single reactant. These are free active sites, and here this one is the total number of active sites. Right? If I have a reaction, say A and B giving product, and adsorption reaction will be A plus S, A dot S, B plus S, B dot S. Right. So, here you can see that CT we can write as CV plus CA dot S plus CB dot S. Right. So, the balance equation will change based on the stoichiometry of the reaction. So, you see that there are two different types of adsorption. If the molecule or adsorbate which is getting adsorbed onto the active sites of this catalyst, if it remains undissociated, right, like adsorption there are two types here from the perspective of dissociation. So, non-dissociative adsorption, but in some cases we have dissociative adsorption. Right. So, if it is a non-dissociative adsorption, say let us say carbon monoxide, it is adsorbed on the active site giving you CO dot S. So, example is carbon monoxide plus nickel catalyst. So, it will be nickel catalyst, and here we will have the adsorption. So, this is the typical example of non-dissociative adsorption. Whereas, if it is a dissociative adsorption, what will happen? CO plus 2S, it will dissociate, this carbon oxygen bond will dissociate prior to adsorption, and it will be giving C dot S plus O dot S, right. And here you see the balance will be CT is equal to CV plus CCO dot S. Here the balance will be CT is equal to CV plus 2 C O dot S or 2C C dot S, right? Because according to the stoichiometry, the number of this type of active site and oxygen adsorbed active site, they are same. Okay, they are identical. So 2C O dot S. So here the example is the adsorption of carbon monoxide again on Rn catalyst. What will be the reaction? So it will be adsorbed. Here we will have the C, here we will have the O. So this is a dissociative adsorption, right? So before we go into that detailed discussion, we must first write the rate expression for non-dissociative and dissociative adsorption, and we will try to fetch out what will be the equilibrium relation. So what is equilibrium relation and what is adsorption isotherm in relation to that, we will discuss later. So first let us try to represent the rate of these both types of adsorption. One is non-dissociative, another is dissociative, right. So we will consider carbon monoxide as a simple example of model molecule. So non-dissociative, first is non-dissociative adsorption, right. So you see that here the reaction, if we consider carbon monoxide, you can consider A or you can generalize it to anything. So it is CO dot S. It's simply A plus S giving A dot S. You can replace it like this. So you see that rate of forward step will be Ka, then carbon dioxide concentration will be represented in terms of partial pressure, and this is the concentration of the vacant site, free sites. So here the rate constant is Ka. Definitely there will be desorption. So that is a backward reaction. So rate of backward step is K minus A C of CO dot S, right. So here the rate constant is K suffix minus A. Okay. So rate of net rate, which is minus Ra, can be written as Ka PCO CV minus K minus A CCO dot S. So if we take this Ka common, it is PCO into CV CO dot S Ka by K minus A. And by definition, this ratio of forward rate constant and the backward rate constant, that's nothing but the equilibrium constant or equilibrium adsorption equilibrium constant. So we define the equilibrium constant Ka capital as small ka by small k minus a. So we have this rate expressed as minus Ra equal to Ka PCO CV minus CCO dot S divided by Ka. Right. So that's the rate expression. Now from here we can think of an equilibrium relation. Right. So adsorption, that is alternatively referred as adsorption isotherm. There is the equilibrium relation for non-dissociative adsorption. Right. So, definitely there the rate of the forward reaction and the rate of the backward reaction will be same. So, in bracket term will be 0. So, we have PCO CV into Ka is equal to CCO dot S as minus Ra equal to 0. Now, the site balance of active sites Ct is equal to Cv plus CCO dot S. So, you see that Ct will be equal to Cv plus Ka PCO into Cv. So, Cv is equal to Ct divided by 1 plus Ka into PCO. So, the adsorbed concentration CCO dot S is equal to this Ka PCO Ct divided by 1 plus Ka PCO. Right. So, that is the adsorption isotherm, right. And then we can convert it to the linear form if we go for the reciprocal. CCO dot S is equal to 1 plus Ka PCO divided by Ct Ka PCO 1 by Ct Ka PCO plus 1 by Ct. So, if we multiply both sides by PCO, so you have PCO CO dot S is equal to 1 divided by Ct Ka plus PCO divided by Ct. Right. So, if I plot in a rectangular graph that PCO divided by CCO dot S versus PCO, right, I must get a straight line fit with intercept equal to 1 divided by Ct into Ka, from which we can count this Ka if we know Ct, and here if you even do not know Ct, from the slope you can get the Ct expression. Right. So, this is the relation for non-dissociative adsorption. So, next let us think of the rate and equilibrium relation for dissociative adsorption. So, the next step or next is discussion will be about dissociative adsorption. So, here you see the reaction will be CO plus 2S giving giving C dot S plus O dot S, right. So, here the forward rate, here Ka, here K minus A, so Ka into PCO into Cv square. Backward rate K minus A C dot S C O dot S, so which is giving you K minus A C dot S square, because following the stoichiometry C dot S and C O dot S are same, right. So, we have the forward and backward rate expressed. So, net rate minus Ra is equal to Ka within bracket PCO Cv square minus C dot S square divided by Ka by K minus A, right. So, we have Ka PCO Cv square C dot S square divided by capital K where this capital K is the adsorption equilibrium constant. Right. So, that is the rate expression for dissociative adsorption. So, what will be the relation for isotherm? Adsorption isotherm. So, you see this at equilibrium minus RA is 0. So, PCO CV square Ka is equal to C dot S square. So, C dot S is equal to Ka PCO under root into CV. Right. Yeah. So, balance of active sites will give you, this balance of active sites will give you Ct is equal to Cv plus Cc dot S plus Co dot S, which is Cv plus 2 Cc dot S. So, we can say that Ct is equal to Cv plus 2 Cc dot S, and Cc dot S is under root of Ka PCO into Cv. So, Cv becomes Ct divided by 1 plus 2 Ka PCO under root. So, obviously, C dot S, this adsorbed site concentration or adsorbed concentration will be the Ka PCO under root into Ct divided by 1 plus Ka PCO under root. Yeah, this one. So, which is equivalent to this. This is for this isotherm for non-dissociative adsorption, and this is for dissociative adsorption. And again we can convert it to a linear form, just like 1 divided by Cc dot S 1 plus Ka PCO to the power half divided by Ka PCO to the power half into Ct. So, 1 divided by Ka PCO to the power half Ct plus 1 divided by Ct. So, if I multiply both sides by this PCO to the power half, yeah, if we multiply both sides by PCO to the power half, so this divided by Cc dot S equal to 1 divided by Ka to the power half into Ct plus PCO to the power half divided by Ct. So, this is the linear form of dissociative adsorption isotherm, and the graph here we will plot this PCO to the power half, and here it will be PCO to the power half by CCS, and we will have a straight line where this intercept is 1 divided by Ka to the power half into Ct, and slope is equal to 1 by Ct. Right. So, from this isotherm analysis and rate expressions, we can get some basic idea of adsorption. Now, if you think of two reactants, right, simultaneously they are adsorbing onto two different sites. So, what will happen then? This is also non-dissociative adsorption maybe. So, here you see that adsorption equilibrium or isotherm for two reactants. So, here the adsorption reaction is A plus S giving A dot S, B plus S giving B dot S, right. So, you see for here the equilibrium is PCO into CV into Ka is equal to K minus A C A dot S. So, obviously, C A dot S will be K capital A into PCO into CV, where we have already discussed about this equilibrium relation. This is K A by K minus A, whereas here C B dot S will be K B similarly into not PCO, P A, right, P A. So, this is P B into C V. Now, from the side balance we have C T equal to C V plus C A dot S plus C B dot S, right. That is the equilibrium relation we have used already. So, C T equal to C V plus K A P A into C T, K A P A into C V plus K A P B, K B into P B into C V. So, obviously, C V equal to C T 1 plus K A P A plus K B P B, right. Therefore, C A dot S is equal to C T K A P A divided by 1 plus K A P A plus K B P B, and C B dot S is equal to C T K B P B 1 plus K A P A plus K B P B. So, these two are the equilibrium relation for individually for this A and B, right. So, next we will think of how to represent the surface reaction. So, okay, let me erase this part. So, the surface reaction. There are two broad models for the surface reaction. One is Langmuir-Hinchelwood kinetics, and another is Riedel kinetics. Here, all the components which are undergoing reaction, they are in adsorbed state. All the participating species are in adsorbed state, right. There may be different type, and here reaction is between adsorbed state species and a gaseous species. One component must exist in the gas phase, another is adsorbed. So, reaction is taking place between these two. So, characteristically these two kinetics are different, right. So, here we have two broad group, one is called the single site mechanism. Right. What is the reaction? A dot S giving simply B dot S. It's adsorbed, it transforms because of this energy rearrangement into product B, which is also in the adsorbed state. So, here you see rate of forward step is Ks into C A dot S, backward rate is K of minus S C B dot S. So, net rate minus R S is K of S C of A dot S minus C of B dot S divided by K capital S. Right, where K of capital S is Ks by K minus S. So, that is the typical single site mechanism. The dual site mechanism, what happens? There are different types. Dual site mechanism. First kind is adsorbed state component interacts with a free neighbor state active site giving B dot S plus S, right. So, that means here we have active site, here is another active site, this, here we have adsorb A, it interacts with these active sites here, right, and it produces B also in the adsorbed state and another active site S, right. So, that is the mechanism of this reaction, and this is the first type of dual site mechanism. So, here you can see that forward rate is Ks C of A dot S into Cv, backward rate K of minus S C of B dot S Cv, net rate minus Rs Ks Cv C of A dot S minus C of B dot S by Ks, right. So, second is the other dual site mechanism. It may be both may be in the adsorbed state, say A dot S plus B dot S giving C dot S plus D dot S. That is also a typical dual site mechanism, because two neighboring sites they are interacting and both are containing adsorbed species, though different species, one is A, another is B. So, here the forward rate is Ks C of A dot S C of B dot S, backward rate K of minus S C of C dot S C of D dot S. So, net rate which is minus Rs Ks C of A dot S C of B dot S minus C of C dot S C of D dot S divided by K capital S, right. So, it may happen that two different types of sites are possible. It is a kind of component, this mixed component catalysis, there is two types of active sites at present. One is represented by S, another is represented by S prime, right. So, like the typical example is the carbon monoxide oxygen reaction over this platinum iron catalyst. Typically what we are talking about, A dot S plus B dot S prime giving C dot S plus D dot S prime, right. This may be a possible case, yeah, this may be a possible case. So, it may also happen like there are different variations, A dot S plus B dot S prime giving C dot S plus S prime. That is also possible. Like the typical example here is platinum, iron, platinum, etc. This is PT, Fe, PT site, Fe site, another PT site. Here carbon monoxide is adsorbed, here oxygen is adsorbed, right, giving to here we will have the dioxide and this is the free iron site, platinum site is still occupied. So, this is S prime, this is S and this is S prime, right, yeah. So, for these two conditions, what will be the net rate? I am writing directly the net rate expression. So, here the net rate minus Rs will be Ks into Ca dot S, Cb dot S prime minus C of C dot S, C of D dot S prime by Ks. And here the net rate minus Rs is equal to Ks C of A dot S, C of B dot S prime minus C of C dot S into this Cv prime divided by Ks, right. And definitely if we have to discuss the site balance, it will be different. So, I am not going into that, right. So, this will be the rate expression. So, possible single sites and dual site mechanisms are this. So, next it is the Ehlers-Danlos kinetics. Here you see one is in the adsorbed state, another is in the gas phase, giving you C dot S. That is also in the adsorbed state, because desorption is yet to take place. Right. So, what will be the rate expression for this type of Ehlers-Danlos kinetics? So, here we have the forward rate Ka C of A dot S into Pb, backward rate Ks here minus S C of C dot S. So, net rate minus Rs is equal to Ks C of A dot S into Pb minus C of C dot S divided by Ks, right. That is the expression for that, and that is the reference to this Ehlers-Danlos mechanism. Now, that is all about the surface reaction. Next, we have a small step, that is the desorption, as you can understand. So, how to represent the rate of the desorption process? So, desorption is just the opposite of adsorption, and let us see desorption process. Here C dot S is giving C plus S, right. So, forward rate, I have used this rate expressions Kd. This is Kd, this is K minus T, right. Forward rate is Kd into C of C dot S, backward rate is K of minus D into Pc into Cv. So, net rate minus R, what I have used, dC, desorption, is equal to Kd C dot S minus Pc Cv divided by Kdc. Right. So, Kdc is the desorption equilibrium constant. See, Kdc is equal to Kd by K minus T. Now, if I think the process in the reverse way, C plus S giving C dot S. So, this is the adsorption process, right. And here this K, what I have notation I have used, Kc. So, Kc is K of minus D divided by Kd. So, in a sense it is 1 divided by Kdc. So, desorption equilibrium constant we can replace by the respective adsorption equilibrium constant. So, minus R dC we can write as Kd into C of C dot S minus Kc into Pc into Cv. So, that is the desorption rate we have here, right. So, in this discussion, except this pore diffusion controlling and external film controlling, we haven't derived the rate expression what we observe from the experiment. We have derived the fundamental rate equations of the adsorption, surface reaction and desorption. So, in the next session we will see that if adsorption is rate controlling, what will be for a specific reaction maybe, what will be the observed rate expression and how we can actually test and determine or confirm that this reaction is adsorption controlled, this reaction is surface reaction controlled and this type of catalysis is desorption controlled, right. So, that is all for this session. Thank you.